Hey chemistry students, in this video I want to clarify why valence electrons are so important for chemical bonding. But before we do that, I want you to verify on your worksheet those practice problems with the Lewis dot diagrams that you've completed them correctly. And just keep in mind the order that we place the electrons. I hadn't quite finished it in over here. I left it incomplete. I had erased some stuff. So the first two on top, 1, 2, then around the side, 3, 4, 5, 6, 7, 8. Those numbers represent which electron gets placed where. Now, it really doesn't matter in a sense if you started on one side or another, like 1, 2, then at that point you would want to spread them out around the thing, and that's the basic idea, you know. So something like that. Normally we start on top, but you don't really have to. We just want to group them up and spread them out in that manner. So if I drew calcium, for instance, like this, that would be perfectly fine. I've got those paired up because they are paired up in the S sublevel. And for potassium, you know, if you put the electron over there, that's not really a big deal either. So this is just to kind of teach the pattern of how you place them, but they don't have to start at the top. But once you place the first one, pair up the second one, and then continue around the rest of the atom. Okay, so even for something like aluminum, right? You know, this is how I drew it on the key, but you know, you could start it like here, 1, 2, and then even put the third one over here or something like that, and that's fine. Okay, the first two get paired up though. Now with that, why are valence electrons so important? Okay, so we're going to learn about ionic bonding today. So ionic bonds occur when a metal transfers one or more electrons to a non-metal, okay, in an effort to do what? To get a stable octet. What in the world makes an octet stable? So I want to analyze that here for a moment. So here's the dot diagram for sodium. It's got 1 electron, 1 valence electron that is, and chlorine has 7. Do you remember the easy way to do that, to figure out how many valence electrons elements have? Right. Here's sodium. It's in group 1A. It's got 1 valence electron. Chlorine, 7A, 7 valence electrons. So it's all about the group number for the representative elements. Now, when sodium passes off that electron, I want to draw it a little bit different than what they've got right here. So off to the side, I'm going to do it a little bit differently, but it's the same type of thing. Here's sodium with its 1 electron, and here's a chlorine atom nearby, and it's got 7 valence electrons, group 7A, okay? And so the electron gets transferred over, okay, boom, and now we've got the ions. Na+, okay, the positive charge is because it's lost the negatively charged electron, and chloride, and I'm going to actually draw chloride with its full octet now. It started off with 7 valence electrons, and now it's got 8 valence electrons, boom, with the negative charge. And so the positively charged sodium ion and the negatively charged chloride ion, those things attract one another, and of course that's how you get a nice crystal of sodium chloride alternating cations and anions of sodium chloride. Okay, I'm not going to draw many more than that, but in a crystal of table salt, you'd have something like that, kind of going off in 3 dimensions. Lots of positively charged and negatively charged things, okay? So let me finish that up, kind of make it complete. That's what a salt crystal would look like, table salt crystal. And each chloride has an octet of electrons. Now, why does that matter? Okay, so let's look at sodium first. Sodium, when it was neutral, had a bunch of core electrons in the first and second principal energy levels. Okay, those were its core electrons, and it had one valence electron in the 3s sublevel. And the chloride, I should say chlorine rather, neutral chlorine, it's got 17 electrons total. I've got to draw a few more sublevels for chlorine. Really just one extra sublevel. There's the 2p sublevel, totally filled up. Bunch of core electrons, and then we've got the valence electrons here in the 3s and the 3p sublevels. And so this is neutral chlorine. I didn't draw that one so well. Let me try again. Neutral chlorine right here. Oh, blue, killing me. There, those had filled up first, and then, okay, so this is where we stand with the neutral atoms. But what happens is, this electron, sodium's valence electron, that is the electron that gets transferred over to the chlorine atom. And when that gets transferred over here, let's think about what happens. In a second, I'm going to erase it and draw it down here. But when this gets moved, we're going to get a positively charged sodium and a negatively charged chloride. Okay, so I'm going to go ahead and move that electron down. It erased a couple of things when I did that. Down here, boom. Okay, and so that electron was here in the 3s sublevel on the sodium, and now it's in the 3p sublevel on a totally different atom. And we've got ions now, because this is a sodium atom with one less electron. Okay? And this is a chlorine atom with one extra electron. So it's negatively charged. Now, what is so special about these ions right here? Well, if you think about it, what we have left right here, and I'm going to highlight it in yellow, the sodium ion, that is exactly what we have in a different atom when it's neutral. That is the same as the electron configuration for neon. Okay? So when sodium loses an electron, and we have this right here, that is exactly the same. It's the exact same thing as neon's electron configuration. Now, remember, neon is a stable noble gas atom. Okay? All the noble gases are very, very, very stable. That's something that I hope you remember after you've left chemistry class. Let me get rid of all this stuff that I wrote on here yesterday. I think I can highlight all of it and then maybe just select here. Come on, highlight all of it. There, okay? So something that I hope that you guys remember is that these noble gas atoms, they're all extremely unreactive. They're all very, very, very stable. You know, even if you don't know why they're stable, you got to recognize that they are. You can't really form compounds. They don't form compounds. Hardly ever. Okay, and actually for a long time, chemists thought that they wouldn't. In the 1960s, I think, somebody made a compound with xenon. And they did that by reacting xenon with the most reactive element on the whole periodic table, and they made a compound called xenon tetrafluoride, which was, you know, people didn't even think you could ever do that. Okay, and I think there's definitely been other xenon compounds made, It's got a really, really big electron cloud with 54 electrons there, and it's kind of easy to get those 54 electrons to move around a little bit. Scientists have also made compounds with krypton, but they've never succeeded making any compounds with argon or neon or helium, and I would put my money on the fact that they will never make stable compounds out of helium for sure, and probably never with neon or argon. They're all really, really, really stable, and so even when they've made compounds with them, it's been very unusual. Okay, and turns out they all have an octet. Neon has an octet, 8 valence electrons. And when sodium loses its 1 valence electron, what's left is neon's electron configuration. We've got an octet in what is now the valence shell, 8 valence electrons right there. Okay? So sodium ion is now just as stable in a sense as a neon atom. Okay, so Na plus is now stable in the same way like neon is. Okay, now what about chlorine? Chlorine has gained that electron, and so we now have 8 valence electrons as well, just in the 3rd energy level. Now it turns out that everything right here, all of these electrons that chlorine ion has now, the chloride ion, that's the same as a different element, also very, very stable. All of this right here is the same. Can you guess? What element has this orbital diagram, this electron configuration? Argon. Argon is element 18 right next to chlorine. Okay, so when chlorine gets 1 extra electron, now it's got 18 electrons like argon. And they're in the same orbitals and sublevels and all of that argon, its electrons are in. Okay, so argon, its electron configuration is what we have now in the chloride ion. Okay, so Cl- is now stable like argon is. Okay, it also has an octet. Okay, so that's sort of the secret here. Getting an octet seems to be what makes ions stable, because when ions become like a noble gas atom, they become stable like those noble gas atoms are. And that occurs when you have an octet of valence electrons and all the valence sublevels are filled. Okay, and in both of these now, okay, all the valence sublevels are filled. Now with sodium, that was accomplished by losing what had been its 1 valence electron, and what we were left with were these core electrons. But now that this electron's gone, those are the valence electrons now. Okay, kind of left over. So what were core electrons? Those have become valence electrons. Whereas with chlorine, 1 extra electron in that valence shell there, and now we've got 8 valence electrons. Okay, so watch this. So what they've done here is they've showed, how you can generate calcium chloride. Calcium is going to lose 2 electrons, and you need 2 chlorine atoms to do that. Okay, so, and I've kind of jumped the gun by drawing that ion there. Calcium is in group 2A. It starts off with 2 valence electrons. It's going to lose its first one to 1 chlorine atom, but it still has 1 other valence electron, but it can lose that one to a second chlorine atom. And so let's analyze that. What's going on here? Okay, well, calcium, when it was neutral, calcium is element 20. It's going to lose 2 electrons to become like argon. Okay? Or another way to think about it is some of the core electrons were just like argon. Remember that noble gas electron configuration? Then we got 4s2. Those are those are the valence electrons that calcium is going to lose in the 4s sublevel. Okay? And meanwhile, chlorine, we could write it out like neon, 3s and 3p. Okay, one of the electrons can go right down here, right? But we got to get rid of another electron, and so you need another chlorine atom to do that. All right, so there's another neutral chlorine atom, but it's ready to take that second electron from calcium, okay? And so now those electrons have been lost. They end up here and here. Calcium is now 2+. This is chloride and chloride, right? And so what elements are those like? Well, now that that electron's gone, we can see that calcium 2+ ion is just like argon. It's stable in the same way argon is. It has the same electron configuration. That should be clear because that's all that's left over. Argon's electron configuration. Now, what about this one? What is neon plus 2 3s and 6 3p electrons? That's also like argon. Okay, so interestingly, in the compound calcium chloride, all of these elements end up with argon's electron configuration once you get the ions there, Ca2+ with chloride, and there's its dot diagram, okay? Boom. Okay, so that's how ionic compounds form, and that's why they form, because each atom becomes stable like a noble gas atom, okay? And so that's why the octet rule is so important, and that's why elements, quote, want an octet. Atoms, they don't really want anything. They're atoms. But when they get the same electron configuration that a noble gas atom has, they become stable just like the noble gas atoms. Okay, so I would like for you guys to work through this. I'm going to give you 2 examples. I'm going to do number 1, and I'm going to do number 4. Walk you through it. Okay, so potassium is in group 1A. It's got 1 valence electron. And fluorine is in group 7A. So it's got 7 valence electrons. Okay, and so, well, what's going to happen? If the metal atom can lose 1 electron, it'll have a noble gas electron configuration. It'll have an octet in those core electrons that are hiding in there. There's already an octet hiding in the core electrons. If we can just get rid of that valence electron. And fluorine, if it gets 1 extra electron, it'll get an octet as well, and that'll be obvious. So now we've got K+ with F- with that 1 extra electron, okay? Now, something else that I want you to do is, instead of merely showing the transfer of electrons, I also would like for you to state what these atoms have become like. What element is K+ like? And that's just like argon. Went from 19 electrons to 18, just like argon. Fluorine, when it gets an extra electron, fluoride, now it's like neon. Okay, it went from 9 electrons total to 10 electrons total with 8 valence electrons. Okay, so I would like for you to also state which noble gas each one of these atoms becomes like. Okay, so sodium. Sodium, 1 valence electron. And oxygen, 6 valence electrons. Okay? And you can see that there's kind of a problem, right? Because as soon as we lose this electron to oxygen, that sodium atom would have an octet in its prior core electrons. That's where the octet comes from. But oxygen here would only have 7. So what we need to recognize is there's, in a reaction between sodium and oxygen, the substances, there's surely lots and lots of sodium atoms available, and so another sodium atom could provide the second electron needed, okay, to make stable ions. So we end up with Na plus and another Na plus, and over here we've got the oxide ion, O2 minus, right, the O2 minus ion. Okay, so what elements are these ions like now? If sodium loses that electron, right, look back at your periodic table. If sodium, here's sodium, if it loses 1 electron, back down to element 10 now, right? Now it's like neon. And the valence electrons would be in the second energy level, the 2s sublevel and the 2p sublevels, right? That's where the octet would come from. So sodium ion is like neon. Okay? So each one of those is now like neon. This one and that one. What about oxygen? So as soon as oxygen gains 2 more electrons, it's also become like neon. Okay? Now, do you remember last semester how we talked about the charges on these ions? Right? You kind of just had to remember that everything in group 1A would become 1 plus, and everything in group 2A would become 2 plus. You had to remember that metals lose their electrons, nonmetals gain some extra electrons. Like, what was all that about? Well, now it should be a little bit clearer. These guys become 1 plus, and these guys 2 plus, and this group 3 plus. Why? Because this group is going to lose 1 valence electron. It only has 1 valence electron to lose, and when it loses it, that atom is going to become like a noble gas. These guys have to lose 2 electrons to become like a noble gas. And these elements, at least the metals right here, well, boron can be a little funny, that whole group really, when they lose 3 electrons, they become like a noble gas as well. All right? And what's the deal with nitrogen's group being 3 minus, and oxygen 2 minus, and fluorine's group, the halogens, 1 minus, and these never forming ions at all? What's the deal? Well, if anything in this group, particularly the nonmetals in that group, when they get 3 electrons extra, they become like the next noble gas atom. And that's why those ions are so stable in that way. Okay? And so, and then the same type of thing for these other nonmetals. When nonmetals gain electrons, they're getting closer to an octet. And when metals lose those electrons, they're moving back down to the octets in their core electron sublevels. Okay? So I'd like for you to finish up 2, 3, and 5. And the assessment online is going to pertain to these questions. Okay, so I will be asking related questions about these problems in here on this page. I'll probably ask some about questions 1 and 4 as well, since I've been talking about them. but I also want you to look at 2, 3, and 4 and try to show how these things are being turned into ions and how those electrons are transferred, and also specify on your page as you work what these ions become like, what noble gases they become like. And then you should be able to answer the questions on the assessment.